Okay, so this is a second part of the lecture, and I will now talk about some list of examples and what to do concretely. So suppose we have B implies not A and not B implies C, so we want to show that A implies C. So we first negate the conclusion not A implies C. So now we replace the 3 into negation conditional rule. So we have A and not C. Okay, so this is equivalent to 3. So we check it. So it means it's we are not using it anymore. So now we check 1 and again using the implication rule. So that means that we need to split this. So not B or not A. So this is equivalent to not. You have to write not B and not A. Not A. Okay, sorry. So from rule 4. Okay, so let's see what happens here. So we branch into two parts. So this holds and then this holds. So we have these two branches. Okay. So now we check 2 and 2 is not B implies C. So again you have to put not here, so we get not B and not C. Okay. But for 2 actually we have A and not A. Okay, so A and not A. So we have a contradiction. So we finish with this part here. Okay, so this part is finished. But this part we were now having into two parts. Okay, so this is actually okay. So this so we divide into two here, and we see not B and not B. So this is finished, and we have not A, not C, and then C. So it's finished. Okay, so every branch is finished by X, so this means this is a valid argument. So let's go to the invalid case where open path arises without this X. Okay, so we have A imply B and not A, then we want to show B. Okay, so this is not valid. So first I have to negate the conclusion, so not B. So we check 1 and it's split into 2, not A and B. Okay, so in case 2 we have we have two branches. So this one and this one, and we have not B B. So this is okay. So we have X, but in this case we are finished. We cannot do anything more because we don't no longer have any implication or disjunction or anything like this. So the point is that it's open and we cannot do anything more. So this is called this is the invalid case, and what we have is not A and not B. Okay, so if you have not A and not B, then if you check, then this is true and this is true, but B is not true. Okay, so therefore this is an invalid argument. So this is a counter example here. Not A, not B is the counter example. So WFF well-formed formula phi is a tautology if and only if not phi is truth functionally inconsistent. Okay, which means it's always false. Okay, so phi is a topology if all the paths in the finished tree are closed. Okay, so if all the paths are closed, so it is a valid conclusion. So as an example, we see that not A or B is equivalent to not A and not B. Okay? And so we want to prove this, so we negate it first. So not of this whole statement. Okay, so we have this, and we use a negated biconditional. So we have a biconditional with negation. So we check it and we split it into two. So not and this and this. Okay, so with this and this. So this two are holding at the same time, and these two are holding at the same time. So we have a splitting into two parts. Okay, so this is the negated biconditional rule. Okay. So in the case one, we have not A or B and not A. Okay, so this is the second case. I split it into two to see it better. So now in case one, we have a so we just follow the case one. Then not, so we just use a not rule here, not rule. And then I use now so for this one we use a negated so conjunction rule, so not B and not A. And now we check this one as well, and we split into A or B case. Okay. So we see that A and not A, so we have X. Okay. And B and not B, X. So this is a valid case. Okay. So now we go to the second part. So we just look at the case 2. So first we check this one here. So to get not A and not B. Okay. So this is a negative disjunction rule first, and then I check this one as well, and so this is negative conjunction rule. So we have we have to split off into two. So we have a not A from here, and then not B. So if you look at it again, so in this branch we have not A, not A, so we get X, and here not B and not B, so we get X. Okay? So this is again a valid argument. So lastly, I will give you some helpful remarks. So do not apply the rules to subformula. So for example, if you have something inside the parentheses, then do not apply here. But when you have some operator outside these parentheses, you apply to there. So also, the order of rules applied does not make any difference, but it is more efficient to apply to non-branching rules. So if you apply to branching rules first, then you have to add to every end of the path, so that makes it exponential growth of the tree. So we don't want to do that, so that's going to make it much bigger work. So this process will eventually terminate. It does not go forever. So that's called decidability. So it is a good property of this test. The soundness is that if you obtain the validity of the test, then we can trust it. Okay? So that's the soundness. And the completeness of the test is that if we obtain invalidity, then we can also trust it. So we don't get we get a counterexample in this case. So this refutation tree method satisfies both of these good properties. Okay, so this is proved by in this book of Richard Jeffrey called Formal Logic. So but we will not show you why that is true, so this is what you can apply to the propositional logic. So, but however, we will realize that this test is not complete if we go to something like predicate logic and so on. So this ends my second part of the course lecture here.